Hello everyone, welcome to the video on the convolution operation. It's the implementation part by Society of Artificial Intelligence or SOAI. Here is the outline. Downloading dataset, downloader in torch.utils, visualizing images, single and multiple convolutional layers, LeNet, LeNet, training on GPU, simple visualization and exercises. So here we should import all the libraries which are torch, matplotlib and numpy. So execute. So our files are importing. So data downloading. So we should download the data. The data is available on the internet which includes images with dimensions 32 cross 32 divided in 10 classes. So here our data is downloading and extracting. So after successfully extracting the data, let's run and execute the cells. Class is train loader. Okay. We use torch vision for computing, compiler vision tasks. Transforms are used to apply function on the downloaded dataset. We replicate the dataset by using the same name. We create a dataset as we can load data locally. We load batches at size 4 by using an iterator and using data iter.next will import both images. Visualize data. We first connect the tensor into numpy images. To plot it, we need to transpose it. So let's execute. It will print type of img, shape and the transpose of the above. It will result 32, 32, 3. Let's print the image. So here we get the image as an output. Then we plot the image. To plot all four images we use torch vision .utils .make underscore grid. Then we print classes for all these images and the classes are ship, cat, truck and ship. Let's move to single convolutional layer. We define class first. It is 20 convolutional. We shape it and run it. This is the variable net which calls the class first CNN and out variable you can see it gives the shape of images. We are gonna print their param values. So these are the values. We get the torch size that is 16, 3, 3 and 3. We now plot the torch size using plt.show. Let's first execute this and finally let's show the output. Now deep convolutional network. We first create a class again with a constructor function with parameter self super function first cnn underscore v2 comma self dot init function self dot model is equal to nn dot sequential function. Here in this we have two values nn dot conv 2d with values 383 and nn dot conv 2d with values 8, 16 and 3. Now there is a function forward with parameter self and x. X is equal to self.model function with parameter x and this function will return x. Here let's execute this value. We get torch size 4, 16, 28 and 28. We take the image, add the channel and denoted the output. Here is the output. Now this is next class which is first cnn underscore v3. Let's execute this. This is very much similar to the previous one. Here torch.size with values 4, 16, 5 and 5 as output. Now show the image. This is our output. Here we write the tensor sizes and we use a 5 cross 5 kernel, and this image is minimized convolutional layer for take out their two-dimensional average. Now LeNet, we again define class. Let's execute this. It's also very similar to the previous one with values, and finally the function forward will return x. Let's execute. We get torch.size with values you can see here, and let's print out. Here we get our values, all the values. Here we use the sequential to build the other part of network. We get 6 channels. We use 10H activation. We use average pooling with downsampling. We taken these numbers into single direction tensor. We define input and output features, and forward function that I had mentioned helps flattening the tensor such it has the same index. Here the tensor values are 1, 1, 1 and 1. Now training LeNet. In this class function, there is a constructor function with parameters self and super function with parameters LeNet, self dot underscore underscore init underscore underscore function. Self dot cnn underscore model is equal to cnn dot sequential function. Here are the parameters you can see in these lines. The average pool 10H, conv 2D, average pool 2D, which I had discussed earlier. Self.fc underscore model is equal to nn dot sequential function with parameters nn dot linear function with values 400 and 120, nn dot 10h function and nn dot linear function with values 120, 84 and nn dot 10h function and nn dot linear function with values 84 and 10. After that, there is a function def forward function with parameters self and x. Here x is equal to self.cnn underscore model function with parameter x, and in the next line here x is equal to x.view function with x.size of 0, -1, and in the next line x.size x.self.fc underscore model function with parameter x, and finally this function will return x. We use cross entropy laws. We use Atom to optimize all the parameters. We use uLearning loop and iterate all the data with forward pass and loss pass. You can see in this output files already downloaded and verified. Now another function, evaluation function with parameter data loader. In this total and correct variables assigned with 0 and 0. In next line you can see for data in data loader, inputs and labels get assigned with value data and outputs is equal to net function with inputs underscore print is equal to torch max function with outputs data 1. Total plus is equal to label store size of 0. Correct plus is equal to print equal to labels dot sum function dot item function. Return 100 multiplied with correct divided by total. Let's execute this cell. Net is equal to LeNet function. Here we keep applying the learning Adam rule. We define loss for we print the accuracy. Let's wait for the output. So now we get our final output. Here you can see when epoch is 0 from 16, the test accuracy is 38.47 and train accuracy with 38.49. And as we move from 0 to 15, test accuracy and train accuracy both gets increasing. And you can see from 38.49 to 66.32, the train accuracy is increases, and from 38.47 to 55.92, test accuracy increases, and we get the output. And here CPU times is user 9 minutes and 4 seconds, system 3.56 seconds, and total is 9 minutes and 8 seconds. Whole time becomes 9 minutes and 8 seconds. So let's move to the GPU. We need to have device variable using CUDA. Let's execute this, and here CUDA. Here the def function with parameter data loader is for evaluation. Again we iterate through the training loop and the labels, and after this the GPU will generate the epochs. Let's execute this function first of all. Net is equal to LeNet function dot to function with device loss underscore function is equal to nn dot cross entropy loss function. Opt is equal to optim dot addm function with net dot parameters function. Here max epochs is 16. Here we iterate I and data in enumerate function with train loader comma 0. As you can see, inputs label assigned with data initially and inputs comma labels with inputs dot to function device comma labels and so on. And finally we will print epoch, and you can see the epoch is printing, and we also print the accuracy. First our epochs gets printed. So here we got our output. Here you can see CPU time is user 2 minutes 8 seconds and system time is 813 milliseconds, and total it become 2 minutes and 9 seconds, which is also a volt time. Here we are calculating the accuracy. Here our test accuracy comes out 56.42 and train accuracy 66.26, which is better than CPU accuracy. Now move to basic visualization. We have LeNet code as written above. We import the 4 images. We run net on these images. We can model access all the layers in sequential order. Here torch.size with values 4, 10. Out.shape it return torch.size with values 4, 6, 28 and 28. We take a particular image and we plot it. Let's move to the another image. We choose the channel and choose the binary color map. You can see here. Now this is the exercise for you. Modify LeNet to work with real U instead of 10H. What is the impact on training time final loss? We have observed overfitting. Use weight underscore decay in torch.optim to add L2 regularization. Instead of Cipher 10, use the managed data available from torchvision.datasets.managed. Download and visualize managed data. But importantly, managed images have only one channel instead of three channels. In this case of Cipher 10, modify LeNet to work with managed, train and find optimized test accuracy. Society of Artificial Intelligence. Thank you.